Hello! In this video, we are going to prove the following theorem. Suppose G is a group and H is a non-empty finite subset of G. If H is closed under the operation of G, then H is a subgroup of G. Now, this theorem is often called the finite subgroup test. And now, let's first remind ourselves of some things. Since G is a group, this means that G is equipped with a binary operation. We have that G is closed under that binary operation. The associative law holds, G has an identity element, and every element of G has an inverse. Now, to prove that H is a subgroup of G, we are going to use the two-step subgroup test, which tells us the following. The two-step subgroup test tells us, given a group G, and H is a non-empty subset of G, if H is closed under the operation of G, and for all A in H, the inverse of A is in H, then H is a subgroup of G. Now, based on what we're given, we are given that H is non-empty, and we're given that H is closed under the operation of G. So all that's left to do is show for all A in H, the inverse of A is an element of H. That will tell us that H is a subgroup of G. Now, before we get into proving this theorem, let's first remind ourselves how exponentiation works for elements in a group. Given a group G with identity element E, and given A is an element of G, then for each integer n greater than or equal to 0, we define the element A to the n as follows. A to the 0 is the identity element, and A to the n plus 1 is equal to A to the n times A, for all integers n greater than or equal to 0. Now, a result that we have proven regarding this is the following. Given a group G, and A is an element of G, we have, for all integers m and n greater than or equal to 0, A to the m times A to the n is equal to A to the n plus n. Okay, so now let's get into proving this theorem. To start the proof, let's first consider a group G with identity element E. Let's let H be a non-empty finite subset of G, and let's suppose H is closed under the operation of G. From here, the whole goal is to show that H is a subgroup of G. And by the two-step subgroup test, all that's left to show is for all A in H, the inverse of A is an element of H. And so to prove this, let's give ourselves an arbitrary element, A in H. And from here, the whole goal is to show that the inverse of A is an element of H. Now, to start, let's consider the following sets. We consider the sets A and A prime. A is the set of all elements of the form A to the n, where n is a positive integer, and A prime is the set of all elements of the form A to the n, where n is an integer greater than or equal to 0. Now, first, we're going to show that A is a subset of H. And we can establish that using induction. So for the base case, we're first going to show that A to the 1 is an element of H. Now, to see how, well, by definition, A to the 1 is equal to A to the 0 times A. Also by definition, A to the 0 is the identity element, but by definition of the identity element, E times A is equal to A. And by assumption, we know that A is an element of H, so this shows that A to the 1 is an element of H. Now, let's suppose inductively, we have established that A to the n is an element of H, where n is an arbitrary positive integer. From here, we want to show that A to the n plus 1 is an element of H. Now, since H is closed under the operation of G, well, since A to the n is an element of H, and A is an element of H, that tells us A to the n times A is an element of H. And also, by definition, a to the n plus 1 is equal to a to the n times a. Therefore, a to the n plus 1 is an element of H. So this completes the induction. So by induction, we have shown for all positive integers n, a to the n is an element of H. In other words, this tells us that A is a subset of H. And since A is a subset of H, and H is finite, well, every subset of a finite set is finite, and that tells us A is finite. Okay, so at this point, we've established that A is a subset of H, and since H is finite, that tells us this set is a finite set as well. So, if we imagine listing the elements of this set, it looks something like this. So we start listing the elements of A, and it goes on forever. But since A is a finite set, this tells us it cannot be the case that every pair of elements in this list are distinct. We must instead have that there exists a pair of elements in this list that are equal. More precisely, our claim is the following. Our claim is that there exists a pair of positive integers, I and j, that are distinct and have the property that a to the I is equal to a to the j. And just to reword this slightly differently, we're actually going to claim with the condition that I is greater than j, because that's fine as well. So this is our claim. Now we're going to prove it. But before we prove it, we're going to be moving back up to the top since we ran out of room, and I'm going to write up some notes up here. So this is our claim. So now let's try to prove it. To prove this claim, well, let's assume for a contradiction, we instead have that our claim is false. Now to reach a contradiction, let's consider the following function. We consider the function f from the set of positive integers to a, given by mapping each positive integer n to the element a to the n. Now let's show that this function is injective. To show that this function is injective, let's give ourselves two arbitrary positive integers, p and q, and suppose p is not equal to q. And to prove injectivity, we want to show that f of p is not equal to f of q. And to prove that, we're going to break this up into two cases. Either p is greater than q, or q is greater than p. Let's first consider the case p is greater than q. Now, if p is greater than q, then it cannot be the case that a to the p is equal to a to the q. Because if that were the case, then our claim would be true, contradicting our assumption that the claim is false. Therefore, we can't have a to the p equal to a to the q. We must instead have a to the p is not equal to a to the q. And by definition of our function, f of p is equal to a to the p, and f of q is equal to a to the q. So this shows that f of p is not equal to f of q. So this completes the case p is greater than q. Now let's consider the case q is greater than p. Well, if q is greater than p, then again, it cannot be the case that a to the q is equal to a to the p. Because if that happens, then our claim is true, contradicting our assumption that our claim is false. So it can't be the case a to the q is equal to a to the p. We must instead have a to the q is not equal to a to the p. And we know that f of q is equal to a to the q, and f of p is equal to a to the p. So this shows f of p is not equal to f of q. So no matter which case we have, it follows that f of p is not equal to f of q. So this shows that f is injective. And now notice, since f is an injective function from the positive integers to a, and a is finite, that implies that the set of positive integers is finite. Because in general, if we're given an injective function f from a to b, and b is finite, then this implies a is finite. So using this result, that's why we're able to conclude that the set of positive integers is finite. But this is absurd because the set of positive integers is infinite. And so we've reached a contradiction. Our assumption that our claim is false led us to a contradiction, and therefore our claim must be true. Another way to go about this is you can also establish that f is surjective to a. And therefore, f is a bijection from the positive integers to a, and because there's a bijection from the positive integers to a, that tells us a is countably infinite, contradicting the fact that a is finite. Right, so you could go about it that way as well. But now that we know our claim is true, this means we can choose two positive integers, I and j, such that I is greater than j, and a to the I is equal to a to the j. And next, notice, since I is greater than j, that tells us I minus j is a positive integer. So, by our definition of exponentiation, we can make sense out of multiplying a to the I minus j and a to the j. If we multiply them together, well, by this preliminary result, we can just add the exponents. So this gives us a to the I minus j plus j, which is just a to the I. But a to the I is equal to a to the j. And by definition of the identity element, a to the j is equal to e times a to the j. So we have established that a to the I minus j times a to the j is equal to e times a to the j. So then by the cancellation law for groups, we can cancel out the a to the j's, so we're left with a to the I minus j is equal to the identity element. And then notice, we know by definition a to the 0 is the identity element. The identity element is equal to a to the I minus j. But again, since I minus j is a positive integer, this tells us a to the I minus j is an element of a. And a is a subset of h, so this tells us a to the 0 is an element of h. So now that we know a to the 0 is an element of h, and we know that a is a subset of h, these two facts tell us that a prime is a subset of h. The reason why is because every element of a prime is either equal to a to the 0 or is an element of a. If we're equal to a to the 0, then we're an element of h. If we're an element of a, then we're an element of h. So no matter what, every element of a prime is an element of h. And so that tells us a prime is a subset of h. Now, since I minus j is a positive integer, well, we know every positive integer is greater than or equal to 1. So I minus j is greater than or equal to 1. Subtracting 1 on both sides, we get I minus j minus 1 is greater than or equal to 0. Therefore, a to the I minus j minus 1 is an element of a prime. And we just established a prime is a subset of h. So this tells us a to the I minus j minus 1 is an element of h. But the claim is that a to the I minus j minus 1 is the inverse of a. And to see how that happens, well, notice if we multiply a to the I minus j minus 1 times a, well, by definition of exponentiation, we know that the exponent here just increases by 1. So multiplying these guys together is just going to be a to the I minus j. And we know that a to the I minus j is equal to the identity element. So when we multiply these two guys together, that gives us the identity element. And that implies that a to the I minus j minus 1 is the inverse of a. Because in general, if we recall, if we're given two group elements, a and b, and we know that b times a is equal to the identity element, then this implies that the inverse of a is equal to b. So applying this result here, that tells us that the inverse of a is a to the I minus j minus 1. And we just established that a to the I minus j minus 1 is an element of h. So this tells us that the inverse of a is an element of h. And that was the whole goal. So from the start, we have shown if a is any element of h, then the inverse of a is an element of h. So by the two-step subgroup test, we can conclude that h is a subgroup of G. And so this completes the proof. And so yeah, that's pretty much it for this video.